Okay, welcome everyone to one of the final episodes for this year, where we are going to work with MPS. I hope you can still all hear me. I did some changes to the audio setup last days. I hope it's still all working out and there are no problems, at least from what I can see on the software. It seems to work out. Okay, we are quite far with our language, and today the topic will be code generators. We will take a look at how code generators work in MPS, what we can do with them, and in our case, we will try to generate some Java code. Not because it's particularly interesting to do that, but because it's quite easy to do with the things that MPS ships by default. And there will also be another stream on Thursday, which is not yet in the calendar, but as I wasn't able to do anything last week on Thursday, where the original topic was interpreters. But I mentioned on Tuesday that we wouldn't do interpreters this year because it's quite a big topic and I would like to have some more time and some more episodes where we can cover this kind of things. So this will most probably happen at the beginning of next year, depending on my schedule and when I have time. So yeah, no interpreters this year, but therefore 2 episodes on code generators. Let's see how far we get today. And then at the end of today's episode, we will take a look at what we can work on Thursday. And Thursday most probably will also include the migration to the latest MPS version. I haven't done that for our project yet, but it's fairly simple to do for a small project like what we have here. So I guess it's a good conclusion of this year's episodes to do that then as well. Okay, so let's take a look at some code. I didn't do anything off stream on the language, so it's still in the same state as on Tuesday. We have our language with the workbook, variables, and tests, and our language can express simple things like variables, asserts, basic binary expressions, greater equals, and things like that. Greater and lower to essentially as well. But you can't really do anything with our language yet. You can't interpret it. You can only write things on the screen and save these programs, but there's nothing you can actually do with the program afterwards. We also have a very basic type system that catches some of the user errors and some scoping for variables. Okay. So that there's just as a small recap on what the language can do. So if we try to like concatenate strings and numbers, the type system complains, etc. If we try to compare variables of different types, also complains. If we say y greater x, for instance, the type system complains that that this is unsupported. So this all still works as we left it on Tuesday. But I just noticed that on Tuesday I forgot to commit and push the changes to GitHub. So let's do that before we actually start today, I guess. Yeah. So what we did is we added statement for executing tests. We refined scopes for variables with hiding name. And I think, oh yeah, and we added some intentions to set the types of variables from the IDE. Set types of variables. Okay, let's commit that. And let's push it. Okay. So it's now on GitHub and we have a clean state where we can actually start working on today. Okay. In general, MPS has two very different kinds of generators. So one kind of generator is what we would typically call model-to-text transformations. So what it does is it takes the program that we have here as an AST and that we store as an AST and basically serializes the AST into text content. This text into text, and this text could happen to be Java. This text could also happen to be C or some other format that we would like to have on disk as files. So that's a way to directly serialize the AST down to some text target. But this is not what we will do today. These model-to-text transformations are useful if you have a language, or are often useful, not always, but in most of the cases they are implemented to take something that is already Java code in MPS and write it into a Java file, or to take something that represents already C code inside of MPS and then write this AST into C files. So the typical use case for this is to take an AST that is already pretty close to the actual text target we want to generate, and then serializes into text that is pretty much on the same level of abstraction as the language itself. It also has some limitations. So in MPS, this model-to-text transformations only exist once per concept in MPS. So there's no way to define multiple text generations for the same concept. So it's in that regard, it's limiting to what you can generate out of the AST there. But usually this is not a real limitations, because there's, apart from the model-to-text transformations, which MPS calls text scan, and what you can create as an aspect for your language, and then here, and then you can define how your concepts should end up in text files. But this is not really a problem, that it has some limitations, because what you typically do in MPS on day-to-day basis when we talk about generators, we usually don't mean model-to-text transformations or text scan. So in MPS, this is typically really referred to as text scan. And it's not something you really use on a daily basis. So MPS ships by default with the Java implementation for this text generation. So there is an implementation of Java inside of MPS that has then the corresponding text generation to Java as well, and this is typically referred to as base language, and this is shipped together with MPS. So this is what you get out of the box, and we will use that heavily today. So what do you do if you don't typically do model to text transformations? You typically do model to model transformations. So what does it mean? That means we take an AST that is represented as an AST inside of MPS. So just like we would open the Node Explorer here, we can see the actual tree of nodes in our program here. We would take that and transform this into nodes of some other language. So we have our basic language here in our test language, but let's for now just focus on the basic language here, which is all the things you see in the workbook here. And what we would like to do is we would like to take all of this and transform this into something that is Java. And as I mentioned before, MPS already ships with an implementation of Java, known as base language. We can do a transformation from basic language into base language of MPS, which is then in the end generated down to Java code. But we don't really care about how we get Java files out of MPS's base language. What we only care about is how we can transform our workbook, for instance, into a Java class. Without doing this on text level, but doing this within MPS. So as a pretty basic example, I will create some Java example solution here. And yeah, let's add this to Git. Let me create a model inside of it, so maybe it gets then a bit clearer what I mean. Or dummy for now. It doesn't really matter. And what we would like to use here is the general purpose dev kit, which includes all of the languages you need to write Java code inside of MPS. Okay, so inside of MPS, we can basically write normal Java code. So we can have a static method main here, for instance, and then define whatever an integer in here, x equals to something like this. So we can already write Java code inside of MPS, and it's also a model. So this is not text what you see on the screen. It's also an AST stored inside of MPS. We can open the Node Explorer and explore the AST here, and then we can see the class contains a member, and the member then contains a statement list, and inside of the statement list there's our variable declaration here. So we already have a way to represent Java inside of MPS. We don't need to do that. We can just reuse that. But what we need to describe somehow is how we can get from our workbook to Java code. And not doing this on a text level, but on a model level. How can we do this? So if we take a look at our basic language here, we can see that apart from the typical aspects like editor, structure, etc., there's already a generator aspect. At the moment, generators and languages have some coupling in MPS. I mean, you can remove it. You can completely remove a generator from a language. But let's for now just assume a language has one generator to make it simple. In practice, you can have multiple and then decide which one to invoke. For instance, if we would like to not only generate Java code from our workbook here, but we would also like to generate C code, for instance, we could do that with the same, with a similar description of the transformations. So what's a generator in MPS. So if we open up the generator here, we can see that there's like a main model in there, and that there's something in here called main as well. And this is what MPS calls a mapping configuration. So how do generators work in MPS and on a pretty high level? So a generator is basically a set of functions that have one input, that is a model element, and one output, that is another model element. But usually the output is from a different language. And then the function with the where you describe how you get from, for instance, a workbook to a class, also has preconditions. The simplest precondition is that it describes the simplest precondition is that the input has to be our workbook here, for instance. So the concept of the model element it can handle has to be of a certain kind. But we can also have more complex preconditions. For instance, define certain properties. So we could assert that we only want to that our generator function can only handle workbooks with a certain name. Makes little sense, but we could do that. Or we could only handle empty workbooks, because we say if the workbook has no content, we just want to not generate anything out of it. So this is the kind of preconditions you can have there. Obviously, you can have much more complex preconditions. But when these preconditions are met, then the generator runtime executes your function that describes how to transform an element in the AST. There are a bit different kinds of these functions, but on a very high level, this is what they do. Some of them can also decide where they would like to put the output. So, but in the default case, you are doing this in place. So we have a workbook that is somewhere in the AST, and we would want to replace it with the Java class at the location where the workbook is. For the workbook, it's simple because it has no parent, right? So it's something. It's a root node. So there's nothing nothing surrounding the actual workbook here. So that would be one transformation. But if we, for instance, say we would like to transform all of the variable declarations here into local variables in Java, then this would happen in place, which means at the same AST location where the where our variable in the workbook language of the basic languages, we would replace that with a local variable declaration. So this is what MPS calls a reduction rule. That means in place where the input is, the output will be placed as well. And then there are some other rules that give you more control about where you want to put the output. Those are called viewing rules. We most probably won't need them today, but I might find some use case for them on Thursday. And then there are also some other kind of rules, like root mapping rules, which is basically the same as a reduction rule. On a high level, there are some details that are different, but it describes how a root is mapped. And maybe we just start with that. So our workbook is a root, right? So what we need to define for it is a root mapping rule. So if we press enter in the root mapping rules section of the mapping configuration, you can see that MPS creates this kind of template for us that we need to fill. So instead of writing plain Java functions or something like that, MPS supports us with a DSL where we can do this in a declarative way. Okay, so we have now created the first route mapping rule here. And now we need to fill out what the route mapping rule is actually operating on. And one thing and that is the concept here. So we have our workbook that we want to operate on. We select the B workbook from the code completion menu. And now from the conditions side here, so everything on the left is basically conditions and behavior. So we could set inheritors to true. That means this rule would also execute for everything that is not exactly a workbook, but for concepts that extend the workbook. Typically, this is not what you want, but in some cases, it can be handy to write a transformation for the super concept and then be able to just reduce the sub-concepts of that. Then there is the condition block. If we press enter there, we get a function where we can describe additional preconditions for this mapping rule. In this case, we don't do anything. We just leave it like it is. And then there's a keep input route, and this allows you to influence how the mapping rule should behave, in the sense of if the input should be deleted or not after this rule was executed. So that means if you have a use case where you want to generate more than one output out of an input, you would set this to false, to true. Sorry. So that would mean after this rule was executed, the input, in this case our workbook, would still exist, and other route mapping rules could define output for it as well. So if we would like to generate a class and, I don't know, an XML file with all the variable names in there or something like this, we could do this with by defining two route mapping rules and setting one of them to keep input to true and the other one to default. And then the route mapping rules would both execute and then create two outputs for us. But in this case, we don't want to do that. So what we want to do is we want to create a class out of the workbook. So now on the left side, we took all of the we took a look at all of the properties we have there. But then there's the right side, and on the right side, MPS asks us for a template. So if we press Control Space here, there's not really much showing up. There's like the main thing here, but what we would like to do is we would like to create a class out of our workbook. So how can we do that? We can press Alt-Enter to open the intentions menu. And the intentions menu here has only a single entry, and that's called New Route Template. So if we select that one, a new window pops up. So the new window in this case, and it wants us to select what kind of route we want to create. And in our case, it's a class, so we just select the class here. And if we now take a look at the left side here of our generator, let me close some of the things here so to get rid of the clutter. We can now see that the generator of the basic language contains two elements. It's the main mapping configuration where we are currently in, and now something called map B workbook. And this is what the intention just created. We can either follow this reference by command click, command B, which is the usual stuff to follow references, or just by double clicking here on the left, and then we get to the actual template definition. And MPS uses annotations heavily to describe what you or how you want to fill the template. So this is our very simplistic template here that is working for our main for our workbook here. So let's see what would happen if we actually execute that. I'm rebuilding the language, which also includes building the generator. And it will take a bit now because I'm rebuilding everything. Okay, so it finished. Now if we go to our sandbox here and we right click on the sandbox model. And oh no, let's go to the workbook here. Oh wait, okay, let's go here and say we would like to rebuild the sandbox. And now we do that. What pops up is the make menu here. And it says rebuild failed because there's like some map workbook Java file here, which cannot be compiled. But it looks quite familiar, right? So this is the name here from the template we defined. Let's do something different and go to the workbook here and right click on it. And then there is a button here, preview generated text. So what seems to have happened is that down here somehow there was a text file written called map_b workbook.java, and then it was fed into the Java compiler. But the Java compiler complains that this is not compilable Java code at the moment. So let's see what the text output for our workbook would be in the end. So let's do a preview generated text here. And then what happens is that MPS gives you a preview of what would end up on disk for the workbook here. So what we can see is it created a class called map_b workbook, which is essentially the same name as the template here. And there's no content in it, obviously, because we haven't defined anything to be content of the class. We only said for each workbook, create one of these one class. There's also a second way to look into what's going on during generation, apart from the preview generated text. So the preview generated text really shows you what would typically end up on disk as, in this case, Java code. But if we want to get an overview about what's happening in the generation that we defined here and to debug it a bit further, there's here on the left side, below the actual modules pool, there's checkpoints. We are not interested in that at the moment. This is something for later. But then there is this add transient stuff. And if we open that, we can see that there is like three kind of models in here. And they all have the same name as our sandbox. So it's basic language.sandbox. And then they have this weird add notation in the end. And what this is it's the different stages that happened during generation. So if we take a look at the zero stage, the zero stage is essentially a copy of the input here. So instead of operating on the things that the user defined, the generator operates on a copy of it because we don't want to destroy what the user has actually written. We just want to transform it into something else. So first thing that MPS does it's copying it for you. And then we can see two more steps here. So if we open one of these steps, in this case, the step 2, we can see that here the content is now a bit different. So there's no workbook anymore. The tests and some other tests are still there because we haven't defined any generator for them yet. But we now have a single class with the name map_b workbook. And then there's another phase here where essentially nothing has happened. Okay, so it seems like that our rule that we defined here was somehow executed. But now we want to change the name of the class, right? So we don't want to have the class to have the name we don't want that the class that we generate in the end has always this weird name b_workbook. We want that the class has the same name as the workbook that we use as the input here. So in this case, we have the my workbook, and I would also like to have that the class that we generate has the same name as the workbook. So to do that, we go to the template definition here. And the template definition up here basically shows you what is the input. In this case, it's the B workbook. And then what's below that is what the output will be. And we could also now just go here and type some other name in the generator, rebuild the generator, and rerun it. And if I now run preview generated text, the name of the class is some other, but it's still just what we described as static text in the template here. So let me undo that like this. Now we need a way to tell the generator engine that in this case we want to set the name of the class here to some value. How can we do that? We can open the intentions menu here. And as I mentioned before, the generator uses intentions heavily for all kind of definitions of what properties to set, etc. So the name of the class is stored in a property. We don't need to know that by detail. I mean, we could go here and take a look at the actual definition of the class concept, which is the MPS implementation of Java. But this is not really useful at the moment. We can also, without further knowledge about the actual structure of the language, we can still write generators. So we don't need to understand all of the details of the Java implementation, how something is named or how the meta model behind it looks like. We can do this here in the generator template. So if we navigate to the name here and we open the intentions menu, there's an entry here called add property macro. And MPS behind the scenes figured out that our cursor was on the name field, and now it has attached this dollar sign here, and has also opened the inspector for us. And in the inspector, which you can't see so good at the moment, so let me move the camera to the top, because this is what will be least interesting today, so that you can see what's going on in the inspector here. So here's the inspector, and in the inspector we can describe how the name is now calculated for our class. And the function to calculate the name gets like 4 values here. One of them is the generator context, which is the overall state of the generation, if you want to call it like that. Then there's the node, which is the actual input, in this case our workbook. And we also get full type system support for that. So we check the type of the node here. We can see that this is a node of type workbook. Then there's also the operation context and the template value. We don't typically care for them. And once we need them, we will take a look at them. Operation context is basically not really used anymore. It was the predecessor of the gen context, if I'm not mistaken. So it's there for mostly historic reasons, I guess, because it also, so it's deprecated, and yeah, it gives you access to all kind of low-level information, which you typically don't want to bother with, and it's deprecated, so most probably going to go away at some point. So what I would like to do here is I would like to set the name of the generated class to the name of the workbook. So what to do is, what can I do to make that happen is So we have the input node, which is our workbook, and then we can just access the name on it. So it has a name property, right? So we know our own meta model, which in this case is our workbook. And if we take a look at the workbook, it implements this inamed interface, and this defines the name. So what I want to do is I would like to tell MPS name the class that you generate after the workbook that was the input. So let's build the generator again and take a look at what the output is now if we click preview generate text here. And now we get a class as before, but the name of the class is now my workbook, which is the same name as the workbook we used as input. Okay, so now the class is still pretty empty, right? We have no content. We basically ignore everything that the workbook currently contains, and only generate a class that is empty. That makes still little sense. So let's fill it with content. So what I would like to generate is, first of all, a main method. So static method main. We have a main method. And now inside of the main method, I would like to place the content of the workbook. I would like to take all of this, all the variables, the if statements, etc., and place them inside of the main method. And I don't care for now that this is not Java code. So the fact that this is still our language and not Java is not yet relevant for us. And in a bit, I will show you why. So, but at the very first thing, what I would like to do is take all of the content of the workbook, place it inside of the main method. MPS has support for doing that, but it's a bit strange maybe at first if you're not used to do it, or if you're not used to the way how MPS handles this. What I will do for now is I will create a variable x in here. It doesn't matter that it's a variable x. It could also be whatever else, because what we would like to do is we would like to replace it. It could also just be an empty statement, right? So we could just have an empty statement here with no content. And now I would like to tell MPS take all of the content of the workbook and place it here inside of the main method. And same as we did with the name, MPS has properties, annotations for doing that. Sorry. So the same as with the property, we get annotations to tell MPS that we would like to describe the actual transformation that is going on. And if we open the intentions menu here, MPS gives us quite some choices. MPS calls, in contrast to the thing up here for the name, that was called a property macro. So a property macro is used to set properties, as the name suggests. In this case, we are setting the name of the class. We could also use some property macro here to calculate the name of the main method, but we don't need that. We want to have it a static name in this case. Now I need to tell MPS take all of the content and place it here. And MPS calls this copy source. And one of the options in the intentions menu here is copy source over node content. And if I select that, MPS creates this the statement in the main method here, which has this this $$ notation, and then copy source. And then down in the inspector, you can see what is actually copied. And in this case, it's the content. We follow the reference, what's the content, and this is the content of the workbook here, which is the statements. So if we, where's my, yeah. So what we tell MPS in this generator rule now is take all of the content and place it inside of the main method. We haven't told MPS how to make Java code out of it, and we also don't need to do that at the moment. If we now build the generator here and we run it again on our workbook, generation fails. Okay, so we get a bunch of exceptions here down in the make menu that it doesn't know how to generate text. For instance, from a variable that we define, or from our expression statement, from the empty statement, etc. So MPS has placed all of our variables, etc. inside of the main method, but then it doesn't know what to do with it. And if we, so these exceptions are all from the final transformation that MPS is doing when it tries to write the Java file. But if we take a look here at the intermediate steps from the generator, and we take a look at the step 2, where before, and we saw that it created our Java class, and we open the Java class, in this case the My Workbook, we can see that all the content of the original workbook is now part of the main method. But obviously MPS has no idea about, or there is no representation of our variables inside of Java, right? So we have no way of putting this into a Java file yet. But what we told MPS is take the content of the workbook, place it in the main method, and now we somehow need to explain how to make sense of these of this content for Java. One naive approach would be to describe it in here, right? To whatever, write code in here that somehow represents this as Java code. Or another approach, naive approach, would be let's just define text generators for all of our concepts. So let's go here and define a text generator for our variable, and then we describe how it should look in Java code. You can do that, but this is also typically not how it's done. So what would you do instead? Just as we described that we would like to create from the workbook a Java class, we somehow need to describe what to do with the other things that we have there. So what we need to do is we need to define more of these mapping functions. And in this case, these mapping functions do not operate on something that has no parent, in this case the workbook, but they operate on nodes that are somewhere under a parent. So AST elements that have a parent. And to describe how to transform them, MPS has a thing called reduction rules. So in the section down here in the main mapping configuration for our generator, we can go to the reduction rules section and then press enter there. And similar to what we get with the root mapping rule, we still get this template which we should fill out. The first thing we need to select is the actual concept we would like to generate. So let's see what we can do. I guess if we take a look at the intermediate step here. So for each variable that we see in our workbook, I would like to generate a local variable in Java. So let's describe how to do that. So the so the concept we are operating on is our variable declaration here, which is b variable. We have no additional condition here, so and we don't set inheritors to true. So we leave everything on the left side after we selected the variable as it is. Okay. So next thing is we need to define how to do the transformation. So what is the result? And in this case, we can so to describe that we need to define a template just as we did for the route mapping. But if we open the code completion menu on the right side here, we can see that there are already quite some options here. While for the workbook, for the route mapping on top, there were essentially no options in the code completion menu. Here we can see that there are already 5 options. The first one is called abandon input. And this basically means delete the input. So produce new output. It's basically the def null of MPS, so to say. So if we would set this to abandon input, and we now make our generator again, and then run the generator for our workbook here by doing preview generate text, we can see that there are a little less errors than before. But this is not what we are actually interested in. One thing you might notice is there is no errors anymore for the b variable as it was there before. But the interesting part happens here in the transient models. Oh, thank you for the raid, Grumpy Game Dev. Hi. So what did you stream, Gerhard? I hope I'm Garrett. Sorry, I hope I'm not butchering your name. So yeah, I'm doing some stuff with a tool from JetBrains called MPS. F sharp. Oh, cool. I'm doing some F sharp in my spare time as well. Cool. So yeah, what I'm doing is I have a tool from JetBrains that is called MPS. It's what you could call a language workbench. So you can define your own programming language with it. I have a pretty simplistic language here, which basically only contains variables and if statements. And right now I'm looking into how to generate some code out of it, not like machine code, but in this case Java code. What is spare time these days? Yeah, sometimes I have vacations, and then I use that time to do other stuff apart from what I do in my day job. Thank you for the follow. And thank you for the follow as well. So what was I doing before? So yeah, I wanted to show that now the variables are gone. So now it looks quite broken here. So you can see that our class does not contain any real content, but all the variables are gone, which is what I wanted to show with this reduction rule here. So that if you set it to abandon input, it basically deletes what you get as the input. But now what we would actually like to do is I would like to create a local variable out of that. So let's do that. the thing I select here from the code completion menu is called inline template. It, as the name suggests, allows you to define a template here right at this location. And now what I would like to create is a local variable declaration. Like this. And let's just have static types and some name here, just to check if it's working. So now out of each variable that our language has, we create a local variable with the same name and integer. Peter, thank you for the follow. And let's run the generator again. So let me rebuild it and now run it on our sandbox again. And let's take a look at the intermediate Java state here. So this is the workbook represented as Java. And now for all variables that were in our input here, so 1, 2, 3, 4, 5, we should have 5 local variables with the very same name. 1, 2, 3, 4, 5. Yes. So now we somehow need to set the name and obviously the type. So let's start with the name first. It's here. Just as we did with the class, we can attach a macro to the name. And then say we would like to assign the name from the input, in this case the variable in our DSL to, or in our own language, to the local variable inside of Java here. So let's see if that works. Let's run it again here. And let's take a look at the intermediate state. Yeah, so now we have variables cy. Let me delete some of the inputs so that we that it's a bit easier to read. So now we have our variables here. Those two. Let's just rebuild and see what's the result. Okay, so we have two variables c and y as we have in our input. The initializer is still gone, and they have all the same type, in this case integer. But we will care for that later. So next thing I would like to do is I would like to initialize those to the same value that we have in the language here. So let's go here and add an initializer, so just as we would. And I. Second. Why can't I add an initializer here? Let's do that in a different way then. So let me define something with the context. Just so yeah. Int x equals okay. Okay, now I see what the problem was. I was not creating the correct statement. Let's redo that. So let's create an inline template. In this case, instead of defining a local variable declaration, we would like to define a local variable declaration statement here. Okay, and now would have a variable. Yes, okay. Int x equals, okay. So now let's set the name correctly again. So here, instead of the hard-coded name x, the variable should have the same name as the input. So this is the node name here. Assign that to the name of the Java variable here. So with the property macro, just as we did for the class name, we can do that. And now I would like to initialize the variables correctly. So in case we have the variable c here, it should be 1 plus, and the initializer expression 1 plus 2, 3, 4, 4, 3, minus 12, etc. So what I need to do to get that working is similar to what we did with the what I did here with the copying over the complete content of the workbook into the Java class. I'm just copying over the initializer from the variable, and to do that, we need to copy the value here, and we can do that with a note from the intentions menu here. Again, just as before, press Alt Enter, open the intentions menu, and then we can select this copy source thing here, which is used to copy something from the input here of the b variable into the output, and this is the initializer. Let's see what happens if we execute that. Run rebuild here. We still get a bunch of errors, but in the intermediate state now, yeah. So yeah, there's some type system stuff going on that is not correct. But what we can see is that now the C and Y are initialized to the same value as they were in our workbook here. Okay. And but we still get some errors here. So if we take a look at the generated text out of that. Okay. Actually, what we see is that we have now 3 variables, but that the initializer cannot be generated into text at the moment because obviously our expressions have now no text again. So what can we do about that? If we go back to our generator definition, we copied now the initializer expression over from our language, what on the screen looks like Java, or similar to to Java code, but essentially it's not the same in the terms of what MPS is expecting here. So what we need to describe is how do we get from our plus to the plus that we would like to have on the Java side. So it was complaining about 2 things, I guess. So the first one was the plus, was the minus expression and the multiplication expression. So just as we described here, just as I described with the variable up here, I would like to describe that a minus expression from our language, E minus, I think, yes, should translate into something in a minus in Java. And to do that, I use a reduction rule as for the variable before. And the actual consequence of this statement is a minus expression, like that. But now we need to tell the generator what we would like to do with the left and the right side, because obviously it complains here. So if we would just add static values here, so 1 minus 2, and rebuild the generator, rerun it here, take a look at the intermediate state. Yeah, okay. Oops, that's not where I wanted to go. I wanted to go here. Okay, now the minus would always translate into a 1 minus 2, but this is obviously not what we want. We want to have the operands there as well. So as we did with the value above here, I would like to copy the left and the right side of our minus down into the Java representation. So I'm using the copy source as well. So I copy the left side to the left side and the right side to the right side, like that. Let's rerun the generator and see what the result is. Okay. So now the minus somehow works, but this is still okay. So we now have a bunch of expressions which we need to translate into Java. So as for the minus, we need to do it for the plus, the multiplication, and the other binary expressions as well. So let me just quickly define them. They look all pretty much the same. Multiplication. Okay. As I did for the minus, I'm just creating those for the plus here. Well, and then describing how to replace the individual operands with left, right. The same for the multiplication down here. Also inline template. And now we do a multiplication x here, 1 times 2, and replace the 2 operands. Let's rebuild. Take a look at what our generator would do out of that. Okay. No, I want to go here. Okay, so this looks good, I guess. Let me run the text generator on this as well. So see what happens there. Okay, so we get a bit further now, so we can see that we have our 2 variables, but now there's a plus here and a minus there, but somehow we have, okay, MPS does not know what to do with our number literals. So let's define a mapping for that as well. That mapping is super simple because each number literal in our language is also a number literal in Java. What's the name of number literal in the language? Let me just quickly check that. So this is what? Integer constant. Okay. So each number literal in our language, on the Java side, it's an integer constant because our language also only supports integers at the moment. Integer constant. Yes. And now we need to somehow define how the value from our number ends up in the value on the integer constant in Java. And we can do that with the property macro as well, I guess. So yeah, if we attach the property macro, it's expecting us to return an integer. Let's see what we have available on the input side. So the node in this case is the number literal. And now we somehow need to extract the value from the number literal. And we have a property for that as well. But we store it as a string, and the Java side expects it as an integer. So let's define an integer. Yeah. Make that part happy. Yeah. Yes, that should work. Let's see if we can make that. We build the generator again and go back to our example. Okay. So we now get some other errors from the Java compiler, but we could actually produce some code out of it. Let's take a look at what it looks like. Review generated text. Yes. Okay, so it looks much better. We have our main function with the two variables, C and Y. And they are also initialized correctly. So 1 plus, yes. Okay. And the second thing, yeah, okay. So let's go back to the actual generator definition here. So what we described with the generator here, the first thing is we described that we want to create out of all workbooks in our, out of each workbook in our language, a class with the same name as the workbook, which is described in this template here. And the name of the class is set to the name of the workbook, which is here in the property macro. And then we have this copy source here, which tells which tells the generator engine copy all of the content from the workbook into the main class here. And now this is still on the same, or this is still of the of our own language definition and not like the corresponding part in Java. So we somehow need to tell the generator how to represent that in Java. We have our variables. This is quite simple. So each variable ends up in a local variable declaration statement here. So everything behind the between those two red T's here is what MPS calls a template fragment. So this is the actual result that this reduction rule produces. For all of our rules that we have at the moment, this looks pretty simple because everything we define in the rule is also the actual result. In some cases, we will need a bit more context to define what we would like to generate in a bit more detail. I don't know if we will get there today, but let's see. So for each variable, we generate the local variable declaration statement. We copy over the initializer. And then we somehow need to define how our plus and minus and multiplication look like in Java. So what I did for that is I defined those 3 rules here. But as you can see, this gets quite verbose quickly. But let's take care of that later. Okay, so I also defined how we can translate the number literal into an integer constant of Java. And now let's take a look what happens if I add another variable that and initialize it to some string value. And I try to generate that. So let's do preview generated text again. And as expected, there is we haven't defined any rule how to represent a string in Java from our language. So let's do that quickly. It's straightforward, the same way as we did for the number literal. So for our string literal, we define a reduction rule and then a template, which is here string constant literal. Here it's called literal. And now if we would execute this, take a look at the text output. Okay, now it's still empty, so we need to somehow copy over the actual content of the string literal, which is here. Similar way as we did for the number literal, we can do that for the string literal as well, I guess. So we can just copy over the value from our string to the actual Java string, like this. Then let's run the generator and take a look at the output if it's now correct or not. Yes. But as you can see, the types don't match here. So if we would feed this into the compiler like this, then yeah, it complains here that our variable is still an integer and that we would try to initialize it with a string. So we somehow need to yeah, our language supports type inference here. So if we initialize the variable, our language can actually infer the type from the initializer, and you don't need to explicitly state it. I mean, you can optionally, but if I would say now C plus Z, then that this is string, so that works. But if we do comparison between them, C greater Z, yeah, then we get the type system error because the inference kicks in and calculates the type for the variable Z is a string in this case because the initializer is a string literal here. So we somehow need to carry that over into the generated Java code. So let's go to the transformation that creates the variable. So it's somewhere here in our main. It's this one. So it takes our variable definition and creates a local Java variable out of that. But we haven't defined how the type is actually set. So the type is always static integer here at the moment. And we somehow need to make this or somehow get this working based on the type that the inference has calculated. How can we do that? So we cannot decide. I mean, okay, one thing we could do is we could add conditions here and then say, okay, node dot type is instance of whatever string or something, string type, and then we would create let's do that actually. So let's move this here. So okay, let's go here and say node dot type. We need to so what we need to do is we have a type that is on the variable here, but I think this one is optional. Yeah, so this is the optional type that you can use to define that a variable has to be of a certain kind, of a certain type. Which you can do like this, I think. Yeah. And if we change this to Boolean, then okay, the type system complains. But this is the type that you can define there, which is not what I want. I would like to. So this is still valid code without the optional type specifier. So what I would like to get is the information from the type system. What is the type that we calculated for this variable? So let's import the type system here so that we can actually try to get the calculated type from the type system. Okay. So now in code completion there are two types. So the first one is our type that we have as the input here from our from what the user defined. But I would actually, so if I would use that one, this wouldn't work. So what I would like to have is the type that we have calculated based on type system information. And I would like to check if this is a string type. So this is our string type. And in this case, I would like to create a string variable. And let's have the second rule as well to show how that could work. I think integer type. No. Number. Int type. Integer type here. And in this case, the variable should int. Like that. So now we have two rules how to create oh yeah, we should also then initialize this with integer. So we get rid of that error. Okay, so now we have two rules how to generate a Java variable out of our variable inside of the workbook. One is if we have a string type and the, if the type of the variable is string, and the other one is how to what to generate out of it when it's actually an integer. Let me rebuild that, and now run the generator on this again. Okay, so that would work. We can distinguish those two cases. The case where we have an integer and where we have a string. But now we are quite hard coding how to generate the variable here based on the type that the initializer has. So one thing I would like to do is I would like to do this in a more generic way. So let me get rid of the second rule here, and let's remove the condition on this one. So instead of describing in the generator rule that we would always like to generate a variable, a local variable of type string or of type integer, I would like to make the type of the variable based on the input. So the two reduction rules that we saw here, so the two definitions of how the generator should handle those variables are essentially the same. So we assign the name and we assign the initializer. But the only thing that is different here is the types. So let's try to encode that into one rule, which is a bit smarter than those two hard-coded ones. Because otherwise, for each new data type that we add to the language, we would need to define how a variable declaration or a variable of that type would look like in the generated Java code. So let's try to generalize that a bit. So we have the string type here. So what if we don't just write the condition based on what the type system has calculated for us, but if we would just insert in the resulting AST at the location where we expect the type that the type system has calculated. So we can do that as well. Okay, let me change this to integer again, just for. Right. Okay, so I would like to replace this string here with the calculated type from the type system. And as we did before, so we have this the macro called copy source, which we can use to insert something into the AST at this location based on the input. So what I would like to do is I would like to replace this string here with the calculated type from the type system. But there's no obvious thing here in the intention menu that would allow that. Well, there is node.type. So if we select that, wait, let me change the name of this one because it's otherwise annoying. So let me change this to declared type. So this is the optional type on the declaration that somebody could the user could add there. Just to distinguish. So we don't want to insert the declared type here. I mean, we can do that and see what happens. Let's do that and do it slow. Okay. So we have now the workbook here, and if we run review generate, okay, we have just a bunch of question marks because so go back to the rule. The rule here defines that we want to insert the declared type, but none of our variables has a declared type. Let's change that here and add a declared type to see and see what happens now. Okay, so at least it complains that it don't know what our integer is in Java. But for the others, where we have no user specified type on the variable, it's still just question marks because there is no declared type on these variable declarations. So let's try to generalize this again and not rely on the declared type. Because our type system already solves this for us. So if we have a variable that has a declared type, the type here is integer. I think it's even integer if we make this an error. Take a look. Yeah. So as soon as the user declares a type, we do not only check if the initializer matches the type. In our type system, the type system also always calculates the type based on what the user defined here. So we can use it in both cases. So in the case where the user has not defined anything and where the user has defined something. So instead of using the declared type, I'm using the type calculated by the type system, which is available under the type property here. So let's see what happens now. Let's run the generator again. Okay. So now all of our three variables complain that there is no way how to represent integers and string types as text. Let's fix that quickly. So what happens now is that the rule here inserts our string and integer types into the Java variable declaration. And now we somehow need to translate this into the actual Java types. Since this is a one-to-one mapping, we can also do this pretty easy with reduction rules. So just as we did for the number literal and for the string literal, we replace our integer type with the Java int. So inline template, and then just integer type here as well. And the same for string type. Inline template, string type like that. Let me build it and run it again. And now preview. Okay. Okay. Now our ints end up as ints in Java as well. And our strings also end up in Java strings. So the compiler should actually be able to read that, right? We have some compilation problem here that we need to have a factor, I guess. Get rid of that. Nope. What? Okay, so for some reason Java compile try something. To give it access to the JDK. No purpose. Oh, let's not do that. Let me remove this again. Let's not add all of Java to this. But just for testing something, I think it can't find that JDK at the moment. So let me add this as a dependency here, just to test it out. So here I would like to depend on the JDK as well, so that we have available for the compiler. Yeah, okay. So that was the problem. So when the compiler was invoked on the generated Java code, it didn't know how to locate the JDK. So what I did as a workaround for now is on our sandbox here, I added the JDK as a first class dependency so that the compiler knows where to find it. But let's try to get rid of that at some point as well. Let's create an issue for that. I don't want to take a look at it today, I think. I just want to finish some of the I just want to finish some of the generator aspects here and not spend too much time on the Java compiler configuration stuff. But I will create an issue in the I don't have a two-factor auth token here at the moment. Okay, I can't create an issue at GitHub because I'm logged out. But let me write it somewhere here in the in my document. When I get my phone, which is in the room next door, I can actually log into GitHub and create the issue there. I'm currently not logged in. Create issue for JDK dependency. Okay. So at least the code that we generate is now compilable. And we have at least some working Java code out of this. I think we can't really, at the moment, we don't have rules how to translate all of our concepts into Java. For most of our concepts, because our language is pretty close to what Java can do. This is intentionally because I wanted to show you something that looks like things you are actually familiar with in daily developer kind of things. So obviously our language looks like many other programming languages with variables, simple binary expressions, etc. Only the surrounding context, like the workbook, etc., looks a bit different. So let's take a look at what we could do today. So as those two languages, Java and our language, are pretty close, these transformations that we define from our language to Java are pretty straightforward and in most cases feel like quite a lot of boilerplate to do, because for all expressions that our language has, we have to define how these expressions look like in Java. And for most binary expressions, this is pretty simple because they look essentially the same. So for these simple transformations, the MPS generator language looks a bit cumbersome or verbose, let's put it like this, because we have to define all of these mappings one by one, while in many cases, if we would look at this from a text perspective, this text on the screen looks essentially the same in a Java file as it looks here in our DSL in our language on the screen. So why can't we just write this text into the same file, and why do we have to define all of these mappings? So we have to define all of these mappings because we are not dealing with text. We are dealing with an AST, and we want to describe how to transform an AST from our basic language into Java. And so in this case, we have to define all of the rules in the generator aspect of the language. So we have it done for minus, plus, multiplication, but there are quite some expressions missing. So if we take a look at the structure aspect of our language, we can see that there's quite a bunch of binary expressions here, which we would need to have. But as this is all more of the same here in this case, I would not like to do this on stream. I will do this after the stream in, like, I don't know, 10 minutes, adding all of these reduction rules for the individual expressions here, so that we don't waste more time on that as well at the moment. But what I would like to build today as the last thing is variable references. So we can reference variables in our language. If we have a variable x, this could reference C and then add Y to it, right? So like that. So this is valid code in our language. If we try to generate Java from that, and say preview generated text. What we can see is that the plus could be translated here, but then for the two operands, we have no rules how to represent this in Java. So what we want to do. So what I would like to do is that in the case where we initialize x from C and Y, I would like to, and we generate C and Y into local variables in Java. We need to somehow tell the generator how to translate that. As before, this is reduction rules. So we take an input, in this case, our B variable reference, and want to translate this into a local variable reference in Java. Input is B variable reference here. And now we somehow need to define the output we want to generate from it. And before, for all of our transformations, we use this inline template here, which if we select it, directly allows us to write the actual code that we want to output from this reduction. But now, well, I mean, we could do that here, right? So we could say we want to create a local variable reference here, I think. Or is it just a variable reference? Variable reference here, yes. Okay, so if we select that from the code completion menu, we are presented with this error here that there is no variable declaration where the reference is pointing to. So this is why we have this error message here, which tells no reference and obligatory role variable declaration. So let's go to the definition of the variable declaration in Java. And the variable declaration in Java has a single reference here to a variable declaration. And this is not optional, so it's so it has here the multiplicity of 1. And now when we write this code here, what we did is we instantiated a variable reference, but we didn't say what variable it is referencing to. So we somehow need to tell MPS how to do that. And to do that, we can use these kind of macros again that we used before. In this case, not for assigning a name, but for setting a reference. So based on the input, so the B variable reference, we want to reference the output that we created for the variable. So if we select the reference macro from the intentions menu here, down in the inspector, as usual in the generator language of MPS, we can define how these references should be resolved. And if we look at the method signature, so let me move it a bit so that you can see everything here. So the method signature has 4 inputs: the node, the generation context, the output, which is what was produced here. In this case, it's not really interesting because our variable reference only has a single reference. But this allows us to work on to take the result of this reduction rule into account when we want to resolve a reference. And this hints at some. So wait, let's start over again. Okay, so we have the node here, the node parameter. The node parameter, if we check its type, like this, we can see that it is the B variable reference, which is the input here. So the left side of our reduction rule. And if we now check what is the output node, let me select it from the code completion menu and calculate the type. We can see that this is just a node, so it has no actual type associated with it. So what is the output node in this case? At runtime, the output node will be the Java variable declaration that we create in the surrounding reduction rule here that defines create out of each variable reference a Java local variable reference. And now the interesting part of this transformation is that the return type here is a join type. So that means we can return one of those three things here. So the first thing we could return is a variable declaration directly. So a node of type variable declaration that we want to set the reference to. The second thing we can return is a string. And the third thing is a node pointer, which is not an actual instance of a node, but all the information you need to find a node in a model. So it's like a serialized a pointer, so to say. We don't need to get into the details there now. But we don't have access to it. So we don't know the variable declaration yet, right? So we don't have the exact instance that we want to point this this reference to here at this point available. But the string looks interesting. So we have the name of the, so if we take a look at the input here, so we have the node. And now our node is our variable reference, which, as the name suggests, has a reference pointing to the actual variable in this case. So here, if we take a look at the definition, the variable reference has a single reference to a B variable. And if we take a look at the B variable, this one has a name through this iname concept thing here. So it has a name, which is what we see here as the name of the variable. And now, what happens if we just return the name or follow the reference to the variable, and then let's just return the name. It's a string, right? So let's see what happens. Let's run this. And let's go here and preview generate text. And it works. So what has happened behind the scenes? So if we take a look at the intermediate step in the generator here. So 2 is where our stuff is actually working. So what MPS has done behind the scenes is, so this is not text. So if we follow the reference here with Command B or Command text, we can see that this is a fully resolved reference in MPS. It's not just some text on the screen, and it's also not parsed, but it's the reference here is really pointing to the AST node int c equals etc. So to the actual local variable declaration. And how did MPS make that happen? So if we type this code, we would also just type C, right? And the code completion menu would offer us to select the actual variable reference. The same what happens in our language here. So if I remove everything and we type C, what happens is that behind the scenes, all of the stuff that we defined with our editor definitions and transformations, not transformations, actions from the UI aspect of our language here, the editor part, kicks in and transforms the letter C that we typed. Let's do it with a big example. My variable, var. So I type my. So at this point, this is still text. So MPS complains that that this is not a valid program yet, because my var is nothing, my v is nothing that MPS that in our my VA is nothing that is that is recognized as an element of our programming language. So with this string that we just entered, nothing really happened from the MPS perspective. So there's no, so MPS doesn't know what my VA means. So we can now either open the code completion, invoke type R again here, right? So like this, and then MPS recognized that string my var here is actually a reference to the variable that was defined earlier here. And now we can also click on it with the command click and then follow the reference, etc. But more importantly, what has happened behind the scenes is that MPS has created this variable reference here for us. And if we take a look at how it looks in the AST, we can see that my var is a variable reference, and that it has a reference pointing to my var up here. So if we follow this, we can see that the AST was constructed correctly. So based on the user input, MPS has figured out that in the AST we need to do this transformation. We need to insert a variable reference that points to the variable with the name that the user entered. And this is essentially the same that happens in the generator. So what we did in the generator is we told MPS, okay, simulate or do the same stuff that you would do as if the user would enter a value here. And the value in this case is the name of the variable. And since our reduction rule up here for our B variable defines that each local variable that we generate has the same name as the variable that was the original input, typing or emulating the typing here at that location, so to say, so typing the name of the variable also resolves it correctly. So we say build a reference here to a variable that has the name of our input, and since the name of the variable that we generate from each input is the same, also now the name of the local variable is the same name as for the input variable in our language. Based on that, we can resolve this reference, right? So if a user in Java would type the name X for a variable X, it would point to the correct local variable declaration up here, X. Let me illustrate that because I guess that sounds quite confusing. So let me just append something to the variable name here. So now each local variable that we generate in Java from our variable declaration has the name of the variable plus underscore something. And if we now run the generator again, this and do this here, what you can see is that it didn't work anymore. So why did this now fail? So the plus here is broken. While before it worked, there was Y and C here. Now this is completely broken. And if we take a look at the log down here from the actual generation, we can see that there is error messages here or warnings here, which are failed to replace reference to a counterpart with the name C and with the name Y. What does that mean? So that means that while executing the generator, we said, okay, find me a variable in the current method. Find me a local variable with the same name as the Find me a local Java variable with the same name as the variable in the original input in our program. But since now there is no variable with the exact same name anymore, because our generator up here for the for translating our variable declaration inside of into a Java local variable declaration appends the name underscore something. So with this string-based resolving, we cannot really find it anymore because there is no variable with the exact same name. So what we could do is we can change both of these rules accordingly. And if we now also append the something down here and re-execute the generators, now it works again because we can now find a variable c something and y something. So what you define in the generator here is not just text, it's real rules how to find the variable on the Java side. So now in this case, our variable reference would depend on the exact same names. I think for now this is totally fine. There are more ways to define how these variable or how these references are resolved in a generator. We won't take a look at that today because I'm getting tired. So this is something I guess we will take, which we should take a look at on Thursday. So what I will do off stream is adding the additional reduction rules for the expressions, because I don't think it makes sense to do that on stream. Add reduction rules for expressions or binary expressions. Expressions. And then on Thursday, we will take a look at refactoring some of the stuff in here so that we get rid of some of the code duplication, especially for the binary expressions here, and how we can make the variable references work without relying on the actual names, but doing it in a more generic way where we don't rely. So currently, if we would change this rule, how the naming of a variable is defined, we also need to change how the resolving works. And I would like to decouple that so that I can freely choose the name up here and don't need to rely on the name when resolving the reference. There are ways to do that in MPS. We will do that on Thursday. So yeah, I guess that's it for today. I hope you like what you saw. If you would like to have a look at the code, you can find the code on GitHub there. And if you like to join the discussion or give feedback, or if you're interested in MPS in general, so it's an open source tool project, mainly maintained by JetBrains, but there's quite a bunch of people around it. We have a Slack instance here where there's also a dedicated room for this kind of streams where you can give feedback and give, but also just join the normal. You can also just join the discussion around the tool, ask questions if you like to try it out. We try to answer all of them there. Or ask questions on Stack Overflow with the MPS tag. I'm personally monitoring it, and other people are doing it as well. So if you try out MPS and you would like to ask some questions there, apart from Slack, you can also use Stack Overflow. And on Thursday, it will most probably be the last stream for this year because I'm traveling a bit for holiday season, visiting my parents and other family members. So I guess I won't be back before New Year's Eve. And if I do a stream, it's very spontaneous. so I don't, I won't be able to really announce it up front. And if we do it, I also won't do much. Yeah, let's see. I don't know what, if I'm in the mood, I might do something. But then we would continue next year with the regular schedule, like Tuesdays and Thursdays. But I think I will only be able to do streams in the first 2 weeks of January, and then not for a month because I will have to travel quite a lot for business reasons. And I don't know which days I'm actually home, so I guess we should check that, and I will write a blog post with the new schedule then. But more importantly than the actual schedule is the content. So if you have things you would like to see, either in the language or in general about MPS, like using certain features of it, how it can be used, or you have like a toy project and or you have a project and you have a problem, just and you would like to have you would like me to have a look at it and to try to solve that problem together, just let me know on Slack or on Twitter, and we can try to figure out if we take a look at the code and do that on stream actually. But apart from that, if you have any features or feedback or in general things you would like to see, post them on Slack or on Twitter. Let me know, and I will try to put this into the streams so that we can take a look at it together. Okay, so I guess that's it for today. I hope you liked what you see, and see you next time on Thursday.